Welcome back, mineralogy fans. Almost everywhere on Earth, the rocks below us are made of silicate minerals. Maybe you have some carbonates or sulfates below you, but go down far enough and the basement rock is mostly silicate minerals. And of that majority of the Earth's crust, almost half are the mineral group we call feldspar, a word with the German roots meaning a field rock with no ore. With feldspars accounting for half of the Earth's crust, another quarter of the Earth's crust is made up of the mineral quartz. Though I like the idea that I once came up with that the name quartz comes from the sound you get when you hit flints or chert pebbles together, it looks like it comes from the Polish twardy, meaning hard, which transformed into the Polish kwarty, which gave the German quarz, which we get quartz. We begin with the feldspars, which all show an appearance of non-metallic vitreous luster. Feldspars, with a hardness of 6, will scratch a 5.5 hardness glass, but just barely. Some force needs to be applied to produce a noticeable scratch. The specific gravity is about 2.55 to 2.76, which is just too common to be of much use, but two good directions of cleavage at 90-degree angles, which causes this mineral to form rod to blocky shaped crystals with irregular ends, is much more diagnostic. Striations, these roughly parallel lines seen in the mineral feldspar, is another diagnostic property of the feldspar minerals, and are actually due to what we call twinning, which is when crystal lattices mirror each other in two separate crystal forms. A crystal of feldspar is really sheets of individual crystals at opposing angles to each other. It gets cumbersome to say calcium-rich plagioclase feldspar versus orthoclase feldspar, so we tend to abbreviate the feldspars. A Ca-rich versus sodium-rich, Na-rich plagioclase is sometimes called Ca-plag or Na-plag, respectively. And orthoclase feldspar is also called potassium feldspar, and since the symbol for potassium is K, you'll often hear geologists refer to this mineral as K-spar. So we will focus on the two endpoints of the continuous plagioclase series and the discontinuous K-spar. The main difference in physical properties of these varieties is their color, though we must be careful here. The most precise identification uses microscope thin sections and chemical analysis, but plagioclase in general is cloudy to translucent white to gray, and K-spar is white to brick red, with the most common color being salmon pink. Color ranges enough in the most common varieties, but there are even odder varieties such as labradorite, whose twinning allows for selective reflection of certain wavelengths of light, or amazonite, whose blue-green color may be due to incorporation of water and lead in the crystal. Those can show you why we must be careful with color. The plagioclase minerals make up around 39% of the mineral mass of the Earth's crust. K-spar makes up another 12%. So the combined feldspars make up 51%, a little over half of the mineral mass of the Earth's crust. Feldspars are economically useful as a mild abrasive or in ceramics as a glaze. A major use is as a fluxing agent for glass manufacture, in which sodium and potassium oxides from feldspar help to lower the melting point of glass-forming agents. And the durability and chemical stability of feldspars make them useful as filler in various industrial products like plastics, rubber, or paints. The next most common mineral, which often gets confused with feldspars, is quartz, being just as abundant as, and often found with, K-spar, as we see here. Quartz makes up another 12% of mineral mass, bringing us a coverage of 63%, almost two-thirds of the mineral mass of the Earth's crust. Like feldspar, quartz is non-metallic, vitreous luster, though it tends to be more transparent than feldspar, though not always. The hardness of quartz is 7, so it can barely scratch feldspar and makes a relatively deeper scratch in glass. The most diagnostic property of quartz versus feldspar is that it doesn't have cleavage. It does have a hexagonal pyramidal crystal habit, but irregular to conchoidal fracture with a total lack of cleavage. Any flat face seen in quartz is a crystal habit face. not a cleavage plane. Remember, feldspars are more blocky with two good cleavage planes at 90 degrees. Though quartz is most common as a gray to white variety, color is not very diagnostic in quartz. It can have a little carbon to make it smoky quartz, or some iron or magnesium to get rose quartz, or some titanium to get amethyst quartz. And an agate is simply all microcrystalline quartz crystals with varying impurities to give all the colors of the rainbows that we can observe. Though large crystals of quartz can be spectacular, we often encounter things like microcrystalline or cryptocrystalline quartz, which make up rocks such as agate, flint, jasper, and chert. Because silicon is chemically similar to carbon, we see wood being petrified by microcrystalline quartz replacement of silicon for carbon. Tiger's eye is an asbestos mineral being replaced by microcrystalline quartz and hematite in what is known as a pseudomorph, when one mineral takes on the crystal habit of another through replacement. Quartz is economically useful for its piezoelectric property of separating charges when stressed, and so can be used to gauge pressure, or you can pass a current through a quartz crystal and get vibrational differences which can be used for frequency control in things like clocks and watches. Historically, the Stone Age is really the Quartz Age, as most stone tools from this time are made of quartz. The irregular fracture can be manipulated into very sharp edges, whereas feldspar rarely has any angle sharper than 90 degrees. In this modern world, quartz is the main component to make glass and silicon chips, and is also a common gemstone in some of its unusual forms. Sand, mined for fracking operations, is made up of countless grains of quartz. And so, right in this episode, we have encountered about 2/3 of all crustal minerals discussing quartz and the feldspars, all within the silicate group that we are not even close to being done with yet. When we come back next time, we will stay in the silicates and examine the minerals from the mafic end of the discontinuous series: olivine, pyroxene, and amphibole.